All right, guys. We are going to start chapter 11, our gas laws notes. I'm going to go ahead and I'm going to do all of these notes at one time, but you don't have to do them all at one time. I'm going to give you guys several days to complete these notes and then turn in the finished product to me just so I can see that you did watch the video and did the notes. All right, so I would start off with saying, if somebody was to come in here and spray body spray into the classroom, what are the particles going to do? And let's say that, and this has happened before, I'm sure you guys have smelled something that somebody has sprayed out in the hallway, and eventually it can come into my classroom. Now, if I were to stand up here at the board and spray some body spray, just one spray even, what are those particles going to do? Well, in your class, if I'm at the board, Maddie's probably going to smell that first, right? And then it's going to eventually go back into the corners to where Noah is and where Molly and Lane and back all through there. So they're going to they're going to disperse and they're going to spread out. So let me do my text box here. They're going to spread out from high concentration, which is where I am. I've got high concentration. I have a whole bottle of this stuff. So it's going to spread out from high concentration to low concentration, until eventually the molecules they're so less concentrated that we hardly smell it. So if I were to spray it, and just one spray, people outside my classroom probably aren't going to smell it just because it's not as concentrated. Now say that I keep spraying it in my classroom over and over and over again, eventually people out in the hallway may smell that. All right, so we're going to look at kinetic theory of gases, and kinetic means energy, like movement energy. So something is moving versus potential energy. It's got that potential to move. So the kinetic theory of gases, it's split up into 5 different things. And movement, how they explain what gases are doing, the movement, is they move rapidly in straight lines. All right, so like the scenario from up above. If I sprayed that, those particles are going to go in a straight line, and as soon as they hit something, then they hit that and they bounce off into another straight line, and it just keeps doing that over and over. Forces. There are essentially no attractive or repulsive forces. Okay, so basically what it's saying is that gas molecules are not attracted to each other. If they were, that would be really strange, because when I would spray that spray from up above, it would travel together and it wouldn't spread out, and you all wouldn't smell it. It might hit one of you and then bounce off of you and hit somebody else, but only one of you at a time would smell it. Just like there are no forces, basically. They just kind of go. They go and they hit something, bounce, and they go in a straight line. The spacing of this stuff, of gases, they are very far apart. Right? Gases, they kind of go all over the place. They fill a container. Whereas solid, like if you're talking about solid, they are spaced, they're very tightly spaced. Like think of anything that's a solid. Now picture a liquid. They are not tightly spaced. They're less than solids, but they're not a gas either where they can just go wherever, right? So if I had a Coke bottle and it was only half full of soda, I would never have that Coke that would be completely fill the bottle. Now if I had a gas in there, it would fill up the entire Coke bottle. Volumes of gases. They have very small volumes compared to the containers they're in, just like the Coke bottle I was talking about. I could have a Coke bottle and I could just blow some air into it, and those gas particles are going to bounce around and fill the entire Coke bottle, but if I were to compact them all down, there really wouldn't be that many of them. And then temperature, kinetic energy. Kinetic energy increases as temperature increases. So we're going to take time looking at different sections of this. There we go. And we'll look at that. We'll look at how temperature affects things. We'll look at how volume affects things, all these different things. So anyways, your kinetic energy, which means the energy of motion, is going to increase as temperature increases, which makes sense, right? Like if I light something on fire, it's going to move quicker. Not only us as people, but gas molecules. All right, so now we will eventually, hopefully we'll all be back, and towards the middle to the end of this chapter, we will do some of these labs here. We'll do a few that aren't on here either. But I want you guys to watch this, and as you watch this, I want you to come up with your reasoning, right? There's no right or wrong to this. I just want to know what you think. So I'm going to go ahead and play this YouTube video, and you guys complete this chart as they go. Now this one is not on your chart, but it is one that we will eventually do. Okay, so here's the first station. It's the first thing that you will write down what you think is happening. And I want you to really notice, look at the air that's from here up. There's air in that dropper. So watch that line, especially where that air is. They kind of zoomed in on it right here. So watch that line as they squeeze. See, that line is no longer there. And watch it, it's kind of hard to see with the hand right there. So just what do you think happened? Every single one of these stations has something to do with gas laws. We just have not learned about any of the gas laws yet, so it's seeing what you guys think before we ever go over it. So basically, why do you think the balloon begins to feel firmer as they hold it over the speaker that's on a pop plate? Alright, now this one, it's going to be really important that you watch the water level. Once they put the beaker on top of this candle, you're going to want to make sure you are watching the water level. That's why they dyed the water red, so you can see it better. Once again, stuff that we will do once we've actually went over the gas laws and you can explain it better. Okay, so the flame has went out. Now you really watch what happens. You can even, yeah, see that pressure go there. So right now they have 60 milliliters of air in that syringe, and it is capped off, so like what's happening is you're stacking books up, and the more books you stack, the more weight there is bearing down on this. And you can see looks to be close. About each book is pushing down about 5 milliliters of air. You gotta think about what's going on with the pressure in that syringe. So this is another one that we'll do in class at some point. And you can see that they're just going to pour some water, not a lot, just pour some water into this soda can, and they're going to heat it up. What they're trying to get to do is the water inside that can to boil. So that's why they're going to put a black backing here in a second. It's to help you hopefully that you can kind of see that there is some steam coming up. That's what they're trying, and you can kind of see it right there on the tab of the Coke. Kind of see that there's some steam coming out. So once it heats up and it's steaming, which means that it's boiling, you're going to pick that Coke can up and quickly put it into the ice bath. You don't want that water inside to cool down, so you got to do it pretty quickly. And the last one, the bell jar. We do not have a bell jar here, but I do have something that works as a bell jar, so you guys will be able to do something similar to this. I have a very large syringe, and you can use a very large syringe and a mini marshmallow and get the same results. So what is happening right now is they're pulling the air out of that bell jar. So what you guys will have is you'll have a syringe, and you'll be able to control how much air you push into that syringe or out. You can see what's happening to the marshmallow. And here in a second, they're going to release all that air. Just open it up to the outside. Once again, you're just trying to fill in this chart, telling me, what do you think happened? Why did this happen? So here's one with just some bubble wrap, and you can see how it's inflating. Once again, they're taking air out. They're taking air out of this bell jar. And you cannot see that happening right now, but that's what's happening. And then once they do that, they make everything back to normal. All right. So anyways, there are some of these we'll do in class, like I said, some we will not, we'll do other things. But that'll be after we go through the gas laws, so that when you do them, when we do see these again and you do them, then you'll be able to explain in your own words exactly what's happening here. All right, the properties of gases. So we have pressure, volume, temperature, and amount. And we'll look at each one of these when we go through each gas law. So for pressure is just the force exerted on walls of a container. Now, it could be any type of container. It could be me blowing up a balloon. It could be a Coke bottle that I'm blowing into, whatever it is. Now, the unit of measure for this, there's a bunch of different units of measure for pressure. The ones that we will see the most and use the most are ATM, atmospheres, or millimeters of mercury, which you may have heard like weathermen talk, use millimeters of mercury. We also see torr, Pascal, two we don't use as often, and there are others. There's like a whole list of units of measure for pressure. Now for volume, it is the space occupied by a gas, and it's normally going to be the space of the container that you're working with. All right, so the unit of measure for volume is going to be the liter or the milliliter. Temperature, it determines the kinetic energy. Now sometimes you'll see me write just capital K, capital E for kinetic energy, and rate of motion. So how fast are these particles moving? The temperature is going to determine that. Now temperature is normally in Celsius, but for when we start doing some of these calculations, it will have to be in Kelvin. Amount is the quantity of gas present. And once again, we could do this in grams. Grams is an amount, how much we have. But for our calculations, we will need moles. All right, so you can see where the problem is going to be, and you guys know what's coming, is they're going to give it to us in grams, and we're going to have to do a conversion to moles. So be looking forward to that. Okay, so this table right here is something you're going to have to use in your homework this week. It's here in your notes, but it's also attached to the homework paper that I will give you guys. So here, the learning check goes with this table. Like this learning check says, what is 475 millimeters of mercury expressed in ATM? Well, it's one of these where I'm going to say, okay, so I've got 475 millimeters of mercury. And then I'm going to draw. Ooh. Oh my goodness, guys. Ooh. Those are my parentheses. I know it's kind of hard to see there. So I'm going to put millimeters of mercury on bottom, and I want ATM, so I'm going to put them on top, and I'm going to use this chart up here. And if you look at this chart, it tells you that 1 ATM is equal to 760 millimeters of mercury. So I'm going to take 475 and divide it by 760, and you will get 0.625 ATM. All right, this next learning check is the opposite. They give you 2 ATM, so I'm going to start off by writing down 2 ATM. Ooh, here we go with my drawing. See if I can do a little bit better. Oh, no, I did not. That is worse. It's my mouse. Oh, my goodness. I'm sorry, guys. My mouse likes to jerk around a lot. All right. So let's see if I can get this line here. Whew. All right. So now I'm going to put ATM down here on the bottom, and I want millimeters of mercury, so that's going to go on top. And just like here, it's still 1 ATM is equal to 760 millimeters of mercury. So I'm going to take 2 times 760, and that's going to be 1,520 millimeters of mercury. All right. So moving on from that, and there will be on that worksheet, there will be some, it may ask you to, it may tell you, hey, you have 475 millimeters of mercury. How many torr is that? If you look, they're the same thing, so always be the same. It might ask for inches of mercury, but you're going to use this to figure out what numbers you're going to place in your parentheses. All right, so using the picture off to the side, explain to me what atmospheric pressure is. So you can see there's a human standing, and you can see this arrow pointing down, and it's gases. If you look off to the side here, it's just a bunch of gas, and it's pointing down, and that's because that is pressure. All right, have you guys ever went up into the mountains and your ears popped, or if any of you have ever flown before and your ears pop? That's because you're getting pressure changes there, right? So if you're using this picture, what I wrote down is it is the pressure exerted by the column of air from the top of the atmosphere. So right now, as you're sitting here, maybe doing these notes, whatever, you have a column of air pushing down on your head, right? It's nothing too crazy, but it's there. What is the normal atmospheric pressure exerted on us? So normally, we are close to about 1 atm. It may be a little less at sea level. Okay, but normally for most of us, it's right about 1 atm or 760 millimeters of mercury. All right, so continuing with that thought, we have altitude, like if you're up on a mountain or if you're down here in the plains, and what the pressure is doing. So look at these arrows. Look, what do you think is happening with pressure? So which location do you think has more pressure? If you're looking at that, I'm going to give you just a second to kind of, you had a thought maybe that popped into your head. And the location that has the most pressure is going to be location B. All right. Were you right? Did you get that right, or did you think maybe it was A? And where would water boil faster? Well, first off, before I even do that, location B has more pressure because look at this. Up here, that pressure of air, it's not pressing down. It doesn't have as far to press down. Over here it does, which means you're going to have more air pressing down on you than you would on top of this mountain. So that's why. So I don't know if you've ever heard anybody talk about boiling water and how it's different if you're in the mountains, but it is. So where would water boil faster at? On location B. And because there is more air pressure. All right, you have less pressure here, and we're going to learn some of this stuff, what happens with pressure and temperatures, which boiling point is all about a temperature, right? So we'll learn more about that coming up. All right, so we are going to watch another video. Once
Grammarly,
again, you guys, you don't have to do all these notes in one sitting. We would have taken 2 class periods to do all these notes.
does more than catch errors. With Grammarly, you can find
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher. But the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Alright guys, so like I said, you may have heard like a weatherman talk about the barometer readings and how heavy the air is. And think of like especially in southern Illinois when we have those humid days, like the air just feels stuffy and there's just more air pressure. So they talk about the barometer readings and all that. So basically how we got, if you go back up and look at this chart where I said 1 ATM is 760 torr or millimeters of mercury, what happens is in a normal area on Earth, we have about 1 atmosphere of pressure from gases in the atmosphere. So if you just have a mercury barometer sitting here, they're looking at the level of this mercury and it's 760 millimeters. So that's where we get that millimeters of mercury and that barometer reading, and we can tell how humid or how heavy the air is. So let's look at this learning check. The downward pressure of the mercury in the barometer, okay, so the pressure going down right here is blank than the pressure of the atmosphere. Now, if you listened in the video here, they said that this would even out, like this would stop when these two things are equal. So it's going to be C, the same. B, a water barometer is 13.6 times taller than mercury barometer, the density, and that shows you the density of mercury is 13.6 grams per milliliter because, well, they put density in there for a reason. Mercury is a lot heavier. Water's density is 1 gram per milliliter, whereas mercury's is 13.6. So the answer is A. Water is less dense. So that is why, covering it up there, but water is less dense. And then that is where we're going to stop, okay? Boyle's law will be the first law we look at for gases and what's happening with these gases. All right, so like I said, this will go on through 2 class periods Tuesday, Wednesday we have no school, so Tuesday and Thursday, we would have been doing notes. You would have gotten a worksheet Thursday afternoon, which I would have said finish up on Friday, and it's on this right here, this is section 1 and 2. All right, if you guys need anything, let me know, and I will see you later.